Hello, chemistry students. This is Professor Sean McMahon, and this is Chapter 8, Gas Laws, and this is the second lecture. With the last lecture, we introduced some of the more basic gas laws like Boyle's Law. Boyle's Law was P1 V1 equals P2 V2. We introduced Charles' Law, which was V1 T1 equals V2 T2. And then we introduced Gay-Lussac's, which was P1 T1 over P2 T2. So again, with Boyle's, the top one, the first law, when we only dealt with changes with pressure and volume, it meant that the other parameters, the amount of gas and temperature, were constant. With Charles, when we only dealt with changes between volume and temperature, that meant that the pressure and the amount of gas was constant. When we dealt with Gay-Lussac's, we dealt with pressure and temperature changes, but volume and the amount of gas was constant. All of these came together to provide us with the combined gas law, P1 V1 over T1 equals P2 V2 over T2. So we've discussed three variables primarily for the basic gas laws with all of these and came together to produce the combined gas laws. Now, in the very beginning, I did a little cheat. I said, look, we're going to be learning the ideal gas law, which is PV equals nRT, where the variable N right here is moles. So that is the last essential piece to get us from these first three laws that combined to produce this equation, okay? And what we're going to use is something called Avogadro's law, where we deal with volume and moles. And we'll see that with Avogadro's law, if I increase the moles of a gas at constant pressure and temperature, the volume will increase. And we could easily understand this by just taking a balloon and me blowing in a balloon, increasing the number of gas particles in that balloon at constant, let's say, room temperature and pressure, the volume will expand. They're directly proportional. So as one goes up, the other does. So I can come up with Avogadro's law. And then what I'll be able to do is combine these two, where I end up getting the ratio that I've been talking about all along, P1 V1 over N1 T1 equals P2 V2 over N2 T2, but really it equals a constant R. So in today's lecture, we are going to derive this constant R so that we can rearrange it to give us PV equals nRT. Now, why is that important? All of these previous laws require initial conditions and then final. So there's a change. So we're not given all of the parameters, we're just given a change, okay? With PV equals nRT, we'll be using this, but now that we know the constants, we don't need a change of conditions to solve for one of the variables. We just need 3 out of the 4 variables. And the variables, again, P for pressure, V for volume, N for moles, and T for temperature. If I have 3 of these 4, and I know the constant, then I don't need a change of conditions. I can just solve for the 4th. So that's going to be the big difference in this lecture. The first lecture, we have some constant conditions and then initial and then a change, which is maybe 2 or 3 parameters. But now we're going to get to the ideal gas law. But enough of that. Let's go straight into it. So how do I go from combined gas law to ideal? They're very close. The difference is the N, the moles. And again, remember the variable N is moles. I know that's a little counterintuitive, but we'll keep it at that. So we need another law to help us create what I've been saying all along, PV equals nRT. And we need one that's discussing moles. It's Avogadro's law. And it's using the concept of kinetic molecular theory. So what we notice is as moles increase, if I have constant pressure and temperature, the volume of the gas will increase. So here we see as the independent variable, the number of mole particles, as a dependent variable, the number of gas. We see that it's a positive slope, it's a linear equation, and we see that they are directly proportional. So how do I make this direct proportionality equal? I need a constant. And then I can solve for that constant, K. So this is assuming that I have constant pressure and temperature as well. Then I get V over N is going to equal some constant that takes in account the constant pressure and temperature. It's always going to equal that. So I'm going to get V1 over N1 equals V2 over N2. So it's Avogadro's law, essentially. So remember, Avogadro's number, moles, 6.022 times 10 to the 23rd. Well, here we're dealing with Avogadro's law with direct proportionality with moles of volume in gases, okay? So we have a direct proportionality as long as pressure and temperature are constant. So now, when I set up this equation, I can actually use it to help me solve for some change in conditions. So what do I mean by change in conditions? I have initial and final conditions. How do I know that? Well, when I read this problem, a 2.9 liter sample of hydrogen gas contains 0.48 moles of hydrogen. How many additional moles must be added to obtain a volume of 6.8 liters? Notice there's no mention of pressure or temperature. Why? It's constant. But I do have a change in conditions. I have initial volume and initial moles. And then I want to know how many moles must be obtained or added to get a new volume of V2. So I'm looking for N2. I want to know how much. Now I see that there's an increase in volume. So that must mean I did what? Put more moles of gas in because they're directly proportional. So what I did here was I rearranged for N2. How did I do that? Again, V1 over N1 equals V2 over N2. Now, if I'm solving for N2, I pretty much have to multiply both sides by N2 to get it out of this denominator. And I would get N2 V1 N1 equals V2 because these would cancel. But I need to get rid of this now. So I need to multiply both sides by the reciprocal. So I'm going to multiply by N1 V1 on both sides. N1 V1. So that's how I got that equation. Now, again, if you don't like that, you can just plug in everything, right? Without doing the algebraic manipulation. Okay? I'm just showing you the algebraic manipulation. You can plug it in directly if you'd like into this equation here, if it's easier for you. But I did. So my N1 was given 0.48 moles. This is 2 sig figs. Why is that? This is a leading zero. Leading zeros never count as significant. And then I have the 6.8 liters, which is my V2, and the 2.9 liters, which is my V1. And I'm left with 2 sig figs, 1.1. The liters units cancel. I'm left with moles, which is what I want. How many additional moles must be added to obtain a volume of that? So in actuality, it's saying how many additional moles must be added. This is just the final moles. So how do I get additional moles? I actually need to subtract the 0.48 moles. Because now that I read this, how many additional moles must be added? I initially started, right? This is my N1. This is my N2. How much did I add? I need to subtract that, right? So when I go 1.1 minus 0.48, now I get a 0.62 moles must be added. However, I have to use my rules of sig figs. I should only go to the 10th. So really my final answer is 0.6 moles are added. That's actually my final answer right there. So in this next problem, if 0.75 moles of helium gas occupies a volume of 1.5 liter, what volume will 1.2 moles of helium occupy at the same temperature and pressure? So this one's a little more obvious. They're telling you that temperature and pressure are constant. Obviously, this is the first mention of moles, first mention of volume. That's my second, so I'm looking for N2. So again, I could, oh, I'm sorry. What volume will 1.2 moles be? I'm looking for V2. Made a careless mistake there, sorry. This is my 1.2 moles, okay? So how do I do that? If I'm looking for V2, what volume, V2, I need to solve for this. I just multiply both sides by N2. So V2, then here's my N2 over N1, V1. And now I can just plug in. So I have 1.2 moles, my N2, divided by the 0.75 moles times the 1.5 liters. 2 sig figs, all of these have 2 sig figs. Again, this leading zero does not count. So I have 2 sig figs in the quotient, and I have 2 sig figs here, multiplying it with the 1.5. So my final answer should be, I need 2.4 liters. Okay, so that makes sense. Moles went up, so volumes must go up because they're directly proportional. Right? Now, if you wanted to plug it in, right? If we wanted to just plug it in, the V1 was 1.5 liters. So I'm just taking this equation, solving for V2. So the VA1 is 1.5 liters. This is 0.75 moles. And then my V2 is what I'm looking for. And this is 1.2 moles. And again, we see if moles go up, this must go up if this quotient is equal to this quotient. You know, you can think of it as if this was 3, 1, and this is 2, this is going to have to be 6 for this quotient to equal the, it's just a proportion. All right. So now that we understand that volume is directly proportional to the number of moles if pressure and temperature are constant, what we could also realize is under similar conditions, right, that the volume of gases have small whole number ratios. So this is a law of combining volumes. So what do I mean by that? Let's look at this reaction here. Hydrogen gas combines with chlorine gas to produce hydrogen chloride gas. Now, to balance this correctly, because I have 2 hydrogens and 2 chlorines on this side, I need to put a coefficient of 2. The reason why this is 1-to-1 is hydrogen chloride. Remember, hydrogens +1, chlorides -1, so it's a 1-to-1 ratio in the formula. So I need 2 moles of it, right? Well, if I have 10 mils of hydrogen reacting with 10 mils of chlorine, it's going to produce 20 mils of hydrochloric acid. It's not always additive, okay? But in this case, because of this coefficient, it is. So what we're seeing is we have these small whole number ratios, right? And that's pretty much what Gay-Lussac discovered. So this is called the law of combining volumes. So how many liters of oxygen react with 38 liters of sulfur dioxide in the production of sulfur trioxide? Okay, so what do I have, right? I want to know how many liters of O2 react with 38 liters of sulfur dioxide. Well, I use the ratio. 2 liters of this react with 1 liter of that. So it's going to be half. It's going to be 19, right? So before we were using 2-to-1 mole ratios when we used stoichiometry. So it's the same thing here. Oh, I guess I didn't. So let me do this. If I have 38 liters of sulfur dioxide, there's 2 liters of sulfur dioxide per 1 liter of oxygen. So I end up getting, because the liters of SO2 are going to cancel as a unit, I'm going to end up getting 19, and I'm going to have 3 sig figs, liters of O2. So just like before, we were doing mole ratios with stoichiometry. Well, now we're doing volume ratios, right? The law of combining volumes. So the volumes of gases can actually be compared under standard temperature and pressure. So what do I mean by that? We can create a set of conditions, STP, which stands for standard temperature and pressure, and then we can compare volumes under these conditions pretty much always. And that way we can do volume ratios. We can think of it that way because it's proportional to the moles. So if we take the same temperature, and the standard temperature is going to be 0 degrees Celsius, remember with gases, everything's in Kelvin. So whenever you see temperature, change it to Kelvin in a gas, always, okay? That'll get you a couple points. The same conditions for pressure, for standard pressure, is going to be 1 atm. So STP, your standard temperature and pressure, are 273 Kelvin and 1 atmosphere. And at this point, this is where we compare gases. And what we notice is that the molar volume of a gas at these conditions, standard temperature and pressure, is basically 1 mole of any gas is going to occupy 22.4 liters. And that's what's unique about gases, is we said that their properties are independent of their identity. Okay, so it doesn't matter if I have a mole of helium, which it weighs 4 grams, molar mass, or a mole of O2 that weighs 32 grams, or a mole of N2, which weighs 28 grams. 1 mole, because a mole is basically the number of particles, is going to occupy 22.4 liters. Why? Remember, the number of particles that tells me the number of collisions. Okay, so you can think of it that way. So 1 mole, doesn't matter what gas, is the same number of particles in all these belong. There's 6.022 times 10 to the 23rd particles, whether they be an atom, an element, or a molecule like CH4. And because with gases, the majority of space, this is what we learn with kinetic molecular theory, is empty space. So the actual volume of the gas is negligible compared to the volume of the container. So it doesn't matter that the mole of helium weighs less than the mole of O2, it's the same number of particles. So the volume that it occupies based on those collisions is the same under these conditions, which is 22.4 liters. So 1 mole of any gas under STP, remember, standard temperature and pressure, which is 273 Kelvin and 1 atm, 1 mole of any gas is 22.4 liters. It's not the same mass, but because it's the same number of particles, it occupies the same amount of space, which is 22.4 liters. Okay, so we're not weighing the gas. I mean, we could, but we're just asking about volume compared to the number of particles. So the molar volume at STP, what is that? It's about 3 basketballs, just to give you an idea. And no one's going to expect you to know that, but just wanted to give you an idea about the size, right? And it can be used as a conversion factor. So I could use it under STP conditions. This is the molar volume. 1 mole of a gas occupies 22.4 liters, or molar volume, mole per liter. So what is the volume occupied by 2.75 moles of N2 nitrogen gas at STP? Well, as soon as they say STP and they want volume, right? Notice there's no change in volume here. There's no V1, V2, N1, N2. So we're not using Avogadro's law because there's no change in conditions. But what we can do is say, well, it's STP under standard conditions of 273 Kelvin, 1 atm. We know that 1 mole of any gas is 22.4 liters. Now, why is that useful? Well, I have 2.75 moles of N2. Well, if I want to know volume, I know under STP, 1 mole of N2 or any gas is 22.4 liters. And then I can solve. The units of moles will cancel. I'll be left with units of liters. And the answer for that, 61.6 liters of N2. So I have 3 sig figs. Why? 3 sig figs in my starting answer. So that's very powerful. That makes it nice. Like if I have standard temperature and pressure, I don't need to use Avogadro's law and have a change in conditions. I can just use this as a conversion factor to get where I need to go. And we see here, the units cancel. So let's go to sample exercise 6. What is the volume at STP? So as soon as you're asking for volume at STP, you should be saying 1 mole of any gas is 22.4 liters. But notice they don't give me moles. What do they give me? Grams of methane, CH4. You don't really need to know that this is methane. You just need to know the formula, okay? So I know if I had a mole of methane, it would occupy 22.4 liters, but I have grams. But what I can do using molar mass is go from grams of methane to moles of methane. And how am I doing that? Molar mass. Getting a periodic table, the best cheat sheet, your best friend in the world. It's not focusing, I'm sorry. And then for moles of CH4, because this is at STP, I can use molar volume of a gas at STP to get liters. They didn't ask they didn't tell the specific unit of volume, like they didn't say milliliters, so just stop at liters. So I'm gonna go 4 grams of methane. If I look, each hydrogen's about 1.01 grams times 4, that's 4.04. And then carbon is 12.01 plus the first. So you're getting about 16.05 grams for 1 mole of methane. And now grams cancel. I go from 1 mole of methane. Because this is STP, there's 22.4 liters of methane. And then I'm left with liters. So we see that the grams of CH4 cancel, the moles of CH4, and I'm left with 5.58 liters of CH4 at STP. And that makes sense because, right, 4 over 16 is roughly 1/4 of a mole. So I have 1/4 of a mole of methane. 1/4 of roughly 23 or 22.4 liters is a little bit less than 6 because 1/4 of 24 would be 6, right? Because 24 divided by 4, 6. So this makes sense. Could we go the other way? Like, could I say, all right, how many grams of helium? So now I know the gas, okay? And the masses can change. We saw that in that very earlier slide because, we had helium, it was 4 grams. We had oxygen, it was 32. And we had nitrogen, it was 28. But the number of particles was the same. So the volume was the same. That's why we can use molar volume at STP. So 1 mole of any gas, doesn't matter if it's helium, it's 22.4 liters, okay? So they are telling me this is at STP, and I have liters of helium. Well, okay, it's at STP, I'll convert that to moles of helium. But wait, they don't want moles. If they wanted moles, I'd be done after 1 conversion factor. They want grams. That's okay, I can go to grams of helium. How? molar mass, the periodic table, the best cheat sheet in the world. So I go 8 liters of helium. There's 22.4 liters of any gas per 1 mole of helium at STP. And 1 mole of helium weighs 4 grams. And I'm not looking at the periodic table, but I'm pretty sure that's what it is. Molar mass. So we see that liters cancel, moles cancel, I get that. And I get 1.43 grams of helium, which makes sense because 1 mole would be 22.4. So 8 liters versus 20 is about, I don't know, it's about a third of it, right? So a third roughly of 4 grams is, 1.43. Yep. All right. So we did Avogadro's law, which was the last law, basic law, V1 over N1 equals V2 over N2. Then we applied the concept of combining volumes and using a standard set of conditions where if I don't have a change, I can still figure out volumes and moles and grams because 1 mole of any gas at STP is 22.4 liters. So now what? Well, what about chemical reactions? We use that law of combining volumes in balanced equations. Well, the volume or amount of gas at STP in a chemical reaction, we can calculate that using these STP conditions and the mole ratios in the balance equations. So we can use those coefficients. That's why balancing is so important. And we can actually perform like a stoichiometric problem. So gases can either be products or reactants in a reaction. So we can use molar volume at STP to help us. Because at STP, 1 mole of any gas occupies 22.4 liters. So as a review, because we did the gravimetric stoichiometry a while ago, I always need a balanced equation. I need to convert whatever units they give me to moles for that substance. And then from moles of that substance, I go to the moles of the substance I want, and then I go to the units I want for whatever substance they're asking. So let's take a look, right? What volume of oxygen gas is needed to completely react with 15 grams of aluminum at STP? Okay, so first, how do I know this is stoichiometric? Okay, well, I'm wanting an amount of a substance when I'm given an amount of a substance in a reaction. So that's what stoichiometry is. They give you an amount of a substance and they want you to determine from that amount how much of another substance you need. So the first rule for stoich is a balanced chemical equation. They gave it to me. Next rule, you're going to convert what? The given units to moles. Okay, what does that mean? I need to convert 15 grams of aluminum to what? Moles. How do I do that? Well, how many grams of aluminum per 1 mole? That's easy. I go to the periodic table and I look, it's 26.98. Okay, that was so first rule, balance equation. Second rule, whatever units they give me, they only give me 1 unit, 15 grams of aluminum, convert to moles. Now convert the moles of the given to moles of what it is they want. Well, what do they want? O2. So I can convert moles of aluminum to moles of O2. So I can convert moles of aluminum to moles of O2. Why? Because in this reaction, it's a 4 to 3 mole ratio. There's 4 moles of aluminum per 3 moles of O2. So that's the third rule. Fourth rule, convert moles of what you want into whatever unit they want. Well, what do they want? They want volume. And because it's SSTP, 1 mole of any gas, so in this case it's oxygen, occupies 22.4 liters. So the steps, I converted grams of aluminum to moles of aluminum. I converted moles of aluminum to moles of oxygen. And then I converted moles of oxygen to liters of oxygen. Why? Because that STP, 1 mole of any gas, is 22.4 liters. So the rules for stoichiometry: balanced equation, check. Convert given units to moles, check. Convert given moles to desired moles, check. Convert desired moles to desired units, check. I guess I rounded up here. It's 26.98. Units cancel. I get 9.33 liters of oxygen gas at STP are required to react with 15 grams at STP. That's how many liters of O2 I would need in this balanced equation right here for aluminum reacting with oxygen to give me aluminum oxide. And this is good review because we're balancing equations. So if we look at this, what type of reaction is this? It's a combination. How do we know it's a combination? Well, I have two things, a metal and a non-metal, combining to do what? Produce one thing, an ionic compound. How do I know that this is an ionic compound? Metal and a non-metal give me an ionic compound. Why? Because aluminums lose electrons. Aluminum, did I say aluminum? Yeah, metals lose electrons. Aluminum's 3+. Why? Periodic table, group 3A. Oxygen's a 2-. Why? Group 6A, 2 away from the noble gases. I crisscross, that's how I get aluminum oxide, and then I have to balance the equation. So this is a good review of stoichiometry, balancing equations, predicting products, identifying the different types of reactions, and now using molar volume at STP. There's more, and we'll do more. How many grams of water, okay, form when I have 1.24 liters of hydrogen gas at STP? Okay, so how do I know that this is stoic? I'm given a certain amount of a substance, and I want an amount of another substance in a reaction. So I'm given what? 1.24 liters of hydrogen gas. I know it reacts with O2, they tell me that, and it produces water. So this is another combination or synthesis, two things combining to form one, okay? But now I want grams. So what are the steps? Balance equation, they gave it to you. I have 1.24 liters of hydrogen gas, okay? Whatever they give you, convert to what? Moles, all right? I have 1.24 liters of hydrogen gas. They tell me it's at STP. What does that mean? 1 mole of any gas, it doesn't matter if it's hydrogen or neon, it doesn't matter, is, sorry, it's backwards. I need to get rid of the unit. Sorry about that, I was getting all excited. I need to get rid of the unit of liter, so that goes on the bottom. 1 mole of hydrogen gas, or any gas, is 22.4 liters. So the liters cancel. Now that I have moles of hydrogen, where do I want to go? Well, I want water. Okay, so I could convert 2 moles of hydrogen to 2 moles of water. If they wanted moles, I'd be done, but they don't. They want grams. 1 mole of water, right, because I have moles, gives me 18.02 grams of water. And then moles cancel, and I'm up for grams. So what did I do, right? I first had a balanced equation. I took the units they gave me and converted it to moles. How? Molar volume, STP. Then I converted the moles of what substance they gave me to the moles of the desired substance. The desired substance was water, H2O. So I did that here. That was step 3. How? I used the balanced chemical equation. Notice me, I write it out. Don't do 1, 1 because people get lazy. They don't look at the coefficients. They always write 1, 1 and you get it wrong. And then the last step, convert the wanted moles, the moles that of the substance you want to the unit. We wanted grams. So I converted it. Could they want molecules of water? Yeah. If they wanted molecules, instead of saying 1 mole of H2O is 18.02 grams of H2O, we would have just said, well, 1 mole of H2O is 6.022 times 10 to the 23rd molecules of H2O. And what if they wanted, they wouldn't want that. But, that just shows you right there. So there's more than one thing that they could have asked for. And if you get it to moles, you can convert it, whether it be grams, milligrams, pounds, molecules, it doesn't matter. As long as we use this mole ratio in the balanced equation, stoichiometry allows us to do that. So here's another one, right? More practice for you. What mass of iron will react with 5.50 liters of O2 at STP? So how do I know that this is stoichiometry? I'm given a quantity of one substance and I'm asked for a quantity of another. I want grams of iron, right? If they gave me moles of iron, I would just use molar mass and I'd be done with, right? If they gave me volume of iron at STP, I could go to grams the way we were doing earlier, but nope, they give me a different substance and it's in a reaction. So I have to do stoich. So first I need a balanced equation, check. Convert the given units to moles. I'm converting, the units they give me are 5.50 liters of O2, and I need to convert it to moles. Good thing this is at STP, because 1 mole of O2 at STP is 22.4 liters. So liters cancel. There's step 2 of stoichiometry. Step 3, convert the given substance that are in moles to moles of what I want. I want eventually iron. So I need to convert moles of O2. I put that on the bottom because I want to cancel it to moles of iron. How do I do that? There's 4 moles of iron for 3 moles of O2. And then I can convert the moles of iron to what I want. 1 mole of iron. Get my trusty old periodic table, and I find iron, and it's 55.85 grams. So I'm just using the steps of stoichiometry that I've been using all along. Convert the given unit to moles, convert the given moles to the moles I desire, and then convert the moles I desire into the unit I desire of grams. So liters cancel, the moles of O2, the moles of iron giving me grams, 18.3 grams. Which again makes sense because 5.5 liters, it's not quite a mole. It's a 3 to 4 mole ratio. So I'm going to definitely get less than, the 55.85 grams. Now, how does this all tie in to what I was saying earlier? Well, the ideal gas law is a relationship of all 4 properties, and we're going to set it equal to that constant. That way, it doesn't have to be under STP. That way, we don't need a change in conditions. We can just have a constant, and we could use that constant. So what are we going to do? Well, we're going to rearrange it to make it look nice, but really, this goes back to what I was saying. PV over NT always equals a constant. So I could have these initial conditions and final conditions. But if I don't have a change in conditions, right? Let's say there's no change, so I can't really use that. I can just set it equal to this constant, and I could rearrange this by multiplying both sides by NT. So what's the universal gas constant R? So let's calculate it based on molar volume under standard temperature and pressure. So I know at STP, the temperature is 0 degrees Celsius, which is 273 Kelvin, because remember, with temperature and gas laws, always convert to Kelvin. The standard pressure is 1 atm. 1 mole occupies 22.4 liters. So if I plug that into the quotient PV over NT, like I have here, I get the constant, the 0.0820. Well, I rounded here for this course. I mean, some classes have it as 0.08206 liter atmosphere per Kelvin mole. Now, here's the thing, though. If you use this constant, you have to have pressure in atmosphere. So you cannot have pressure in millimeters of mercury. So you'll have to change it. How? 1 atmosphere is 760 millimeters of mercury. You cannot have the volume in milliliters. It has to be in liters. That's okay. We have the metric system. There's 1,000 milliliters in 1 liter. You cannot have the temperature in Celsius. That's okay. Kelvin is Celsius plus 273.15. So, and you can't, I mean, this, if they give you grams, you need to convert it to moles to get this unit. So if you have the units, it'll work out. So what exactly does an ideal gas mean? I mean, what's ideal? Okay. So the ideal gas law works when gases behave ideally. So there's a certain parameter for what's considered ideal. So the volume of the gas particle must be small to the volume of space it occupies. So typically when you have large volumes or lower pressures, if you have really small volumes and extreme pressures, the ideal gas doesn't work as well because now the gases don't have a lot of room to move and have their kinetic energy, and they start to stick more, right? Because they're really close. So the ideal gas doesn't work well under extreme pressure, okay? It also doesn't work very well if it's really cold, because if it's cold, they're moving slower. And if they collide, they might start sticking. We actually see that with condensation when we have like a cold drink on a humid day on, on the table. If some water vapor hits that can and transfers some of that kinetic energy to the can, causing it to vibrate more, now it slows down. And then if another one hits it and it starts slowing down because it's moving slower, it starts to condense. So the ideal gas is not under extreme pressure or extremely low temperatures. Other than that, this gas law works pretty well. Okay. For purposes of this course, we are going to use the ideal gas law. There is another gas law. It's called the real gas law formula. It's a little more complicated. For purposes of our course, we're not going to deal with it. Okay. In other courses where there's extreme conditions, you will use that. Okay. But for this one, we're not. So can we use PV equals nRT effectively? Well, let's see. Calculate the volume. So let's say you're reading a homework problem and you see volume. You might say V1 because you might be thinking this might be Charles' law or Boyle's law or the combined gas law. That's fine. Calculate the volume. I'm looking for volume that occupies 0.845 moles, okay, N1, of a nitrogen gas at pressure 1.37 atmosphere, P1, and a temperature at 315 Kelvin, T1. What I notice is there's no change in conditions. There's none. But what I do have is I have 3 of the parameters out of the 4, right? The only parameter I don't have is volume. That's what I'm looking for. But I have moles of the gas, pressure, and temperature. That's why I can use the ideal gas law, because this constant allows me to solve for the volume. So I have to plug it in. They were nice. They gave me moles because the ideal gas law constant is moles. It has that unit. They gave me atmosphere. They could have given me millimeters of mercury. They gave me Kelvin. They could have given me degrees Celsius. So this problem was nice. It's not always nice. We'll work towards it. So what I could do is, to solve for volume, divide everything by P. So it cancels. I'm left with volume is nRT over P. I plug in for N, my moles. Notice the R. What are the units? Liter, atmosphere, mole, Kelvin. That's why I need what for temperature? Kelvin. And then for my pressure, I need what? Atmosphere. I notice that the moles cancel, the Kelvin cancel, the atmosphere leaving me with liters, and I get 16 liters. I have 3 sig figs. Why? 3 sig figs, 3 sig figs, 3 sig figs. This is a leading zero. Leading zeros don't count. I don't use my constant for sig figs. I'm not going to use it. Okay. For my class, do not use the constant for sig figs because you're bringing it in. Just use the numbers in the problem. So, can I solve for the following problems using the ideal gas law? The homework's not going to tell you use the ideal gas law. They're not. My quizzes and exams won't, but you could still figure that out. How come? I have a cylinder that contains 5 liters. So you might say, all right, this is V1 of oxygen at 20 degrees Celsius. That must be T1. And an atmosphere at P1. How many grams of oxygen are in the cylinder? Okay. V1, T1, P. Okay, so I want grams of oxygen, right? But I'm given a gas. I have volume, temperature, and pressure. There's no change in conditions. No change. So when there's no change in conditions, you got to use PV equals nRT. Well, what do they give me? They give me pressure, they give me volume, they give me temperature, and R is a constant. Can I solve for moles? Yes. If I know moles of O2, because remember, oxygen's a diatomic in elemental form. If I know the number of moles, can I convert to grams? Using a periodic table, yes, because we can use molar mass, the number of grams per mole. So PV equals nRT. I'm going to rearrange and solve for what? Moles. How do I do that? Divide both sides by RT. So moles equals PV divided by RT. Now, I skipped a lot here. What did I skip? Well, I didn't skip that much. I plugged everything in, right? So for pressure, what did I plug in? 0.85 atmospheres. I was lucky they gave me atmospheres. And why? Because again, my constant pressure units are atmospheres because we want that to cancel. I was also lucky they gave me for volume liters, right? Why? Because I need the liters to cancel. What they did not give me was Kelvin. So what I didn't show you for temperature, what did I have to do? I had to go 20 degrees Celsius, and I had to add 273.15 to get it to Kelvin. When I do this, I get 293.15 Kelvin. But this goes to the tenths, so my answer has to go to the tenths. Because in the hundredths place, there's a 5, I'm going to round up, and that's where I got the 293.2 Kelvin. So now the Kelvin cancel, and I'm left with basically 1, because on top there's nothing, over 1 mole for a unit. So my unit's mole, but when I plug in the numbers, I get 0.1766 moles of O2. Now, I didn't do sig figs yet because I'm trying to avoid round off error. I know that my answer is only going to have 2 sig figs, 2 sig figs. This actually ends up being 4 sig figs because when we do addition subtraction, we don't go 3 sig figs. We use a precision. And once I add it, I see that I've increased the number of sig figs to 4. So this is 4, this is 2, this is 2. We don't use this. My final answer should only have 2 sig figs. But I'm not going to round. Not yet. I'm just remembering my final answer as 2 sig figs. That's why I'm underlining. But now what am I going to do? I'm going to go moles to grams. How? Well, in 1 mole of O2, there's 32 grams. Moles cancel. I multiply the 0.1766 times 32. So I go 2 decimals beyond where the sig figs are supposed to end. That way there's no round off error. And I get a final answer, because I want 2 sig figs, of 5.7 grams of O2. So I'm using the ideal gas law constant to get moles, because once I have moles, I can use what I learned in previous chapters, like how to go from moles to grams using molar mass. So again, use the ideal gas law to solve for molar mass in the following. Now, they may not tell you that, okay? They might not tell you, use the ideal gas law. They'll just say solve for molar mass, okay? And that's okay. What is molar mass? Molar mass is grams per mole, right? That's what we did. We would go to the periodic table, add up, the average atomic mass, use a unit to grams to get a mole, molar mass. So I need to get molar mass grams over moles. Well, let's read. A sample of gas, I don't know what it is, because if I did, I could just look it on the periodic table. But I do know that this sample of gas is this many grams. Okay, I have grams. To get molar mass, what do I need? I need moles. They're telling me it's a gas. Okay, what else? Its volume is 0.31 liters volume. Temperature 65 degrees. There's my temperature. Pressure 924. Okay, so this is my pressure. Find its molar mass. They're giving me pressure, volume, and temperature. Pressure, volume, and temperature. Can I get moles so that I plug it into this? Yes. Using PV equals nRT, and I have the luxury of the gas law constant. So what do I need to do? Solve for moles. Now, temperature. What do I need to change temperature to? Kelvin. How? Add 273.15. What do I need to change millimeters of mercury to? Atmospheres. How? Divide by 760. So I guess I didn't show every step, but I could show that. Your pressure, 924 millimeters of mercury. What am I going to do? There's 760 millimeters of mercury for 1 ATM. That answer is right here. Okay? So it's in red for you. Now, I put more than 3 sig figs. Why? I'm trying to avoid round off error, right? So here's 3 sig figs. I did one more. They gave me liters. How did I get 338? 65 degrees Celsius. So 273.15 plus 65, right, is 338.15. This went to the ones place. So I put the 338 right there. Now, I solved for moles. I have moles. My final answer is going to have 3 sig figs. Why? 3 sig figs here, even though right now it's 4, but I didn't want to round. 3 sig figs, 3 sig figs. So I underlined 3 sig figs. This is my moles. So for molar mass, grams per mole, divided by the grams, 0.244 grams, by the number of moles, and I get 3 sig figs for my final answer. The molar mass of this gas is 18 grams per mole. I wonder if that's water vapor, right? 18 grams per mole, could be. We don't know, you know? So this is kind of the end of this particular lecture. In this lecture, we introduced Avogadro's law and the combining of volumes in balanced equations where we did volume ratios. And then with Avogadro's law, we use those volume ratios relative to mole ratios so that we could get stoichiometry done when we could do stoichiometry under a set of conditions where we know how much 1 mole of gas occupies. So we created a standard temperature and pressure. Standard temperature, 273 Kelvin. Standard pressure, 1 atmosphere. 1 mole of any gas, 22.4 liters. So from that, we were able to do a lot of molar volume types of calculations. We took Avogadro's molar volume calculations and Avogadro's law, combined it with the combined gas law, and created ideal gas. And the ideal gas, there's no change in conditions like all the others. Boyle's, Charles, Gay-Lussac, Avogadro's. There was initial and final. Here there are none. So because we're using a constant, you have to make sure that we're only given 3 variables. Those variables agree with the constants in, or those variables, those parameters, those units agree with your constant. So pressure needs to be in atmosphere, volume needs to be in liters, temperature must be in Kelvin. And then from PV equals nRT, we can not just solve for one of the 3 parameters, but we may even be able to solve for something like molar mass or density. Okay. But thanks for tuning in. That is lecture 2 for chapter 8, gas laws. And thanks for watching. And we'll have one shorter lecture 3 for the remainder of gas laws, where we can show stoichiometry in non-STP conditions. Thanks so much.